Okay. Well, thanks everyone for joining today. I'm grateful for James to inviting me to present. I've been following the effective environmental movement for some time now, for about 7 years, and it's nice to see how the movement has grown over time. So let's begin. First, a bit about the National Renewable Energy Laboratory where I work, known as NREL. NREL is one of 17 research labs funded by the US Department of Energy. It was founded initially as the Solar Energy Research Institute in 1977 and has developed many of the technologies that have made renewable energy as cheap as it is today. NREL has about 3,000 full-time staff and about $500 million in annual funding. I need to inform you that much of the research I'm presenting was performed at NREL and funded by the US Department of Energy. The views and opinions presented today are my own and do not necessarily represent the views of NREL, DOE, or the US government. There is a lot to cover in the climate space, and I can't begin from the basics, so I'm expecting you to have some basic knowledge on climate and energy. I expect you to know the greenhouse effect and primary greenhouse gases, understand the difference between power and energy, care about climate impacts, and be familiar with the basic ideas of effective altruism. Is there somebody that wants to volunteer to explain the difference between power and energy? That's an important concept. James, do you want to take a go at it?
Hopefully. I study physics, so you think I'd be all right. Well, very broadly, power is energy over time. So essentially, how do you define it? Yeah, I guess, I don't know, besides that, in terms of power is the rate of energy change rather than energy is just like a cumulative thing, yeah, over time. It's a really terrible definition, but I don't know what context you want it in, but yeah. Yeah,
no, that's great. Yeah, yeah, we can have like high instantaneous power, which is a high rate of energy transfer. So things that are exploding, for example, or things that have a lot of energy. So a very hot cup of water has a lot of energy in it, but you can't necessarily get much power out of that. So scoping out what we'll be talking about today, annual global greenhouse gas emissions are about 500 billion tons of CO2 equivalent. Nearly 3/4 of emissions are energy related, and 1/3 of that, or 1/4 of the total, is from electricity generation and heat used in buildings. My presentation today will focus on the electric grid and commercial and residential buildings, which constitute about 75% of electricity use. Electric vehicles are the primary means of decarbonizing the transportation sector, and several industrial processes can electrify as well. Much of the remaining energy emissions may be displaced by hydrogen or other synthetic fuels, which can be produced with renewable electricity. So while my talk today is limited to buildings in the grid considerations may end up impacting most energy-related emissions. 2 years ago, I gave a talk to this group on fluorinated gases used as refrigerants, which is somewhat related to buildings. I won't have time to go over that today, but I'll drop a link to that presentation in chat for those who are interested. And let's see if I can do that really quick.
And note on that is I'll send up a follow-up email with a bunch of links that Matt drops into the chat. So plus the recording, so you will get follow-up with all this stuff. FYI.
Yeah, I might drop them in at the end, so I don't have to pop out of the notes here. Okay, great. The main motivation for my talk today is to improve energy literacy and numeracy in the effective environmentalism community, especially around electricity production and use. There are many old and new electric generation and storage technologies competing for a role in the decarbonized grid of the future. They are supported by a range of public, private, philanthropic, and government funding. If you are in a role of providing that funding or are considering going into a grid technology related industry, I hope to learn something new about the energy transition today. 75% of electric use occurs in commercial and residential buildings. So if you want to understand electricity demand and how it may change in the future, you need to understand buildings. Before I get into the details of building energy use, it's helpful to understand some basic thermodynamic principles. Psychrometrics is the study of thermodynamic properties of gas-vapor mixtures. For heating, ventilation, and air conditioning systems, abbreviated as HVAC, the most important mixture is air and water vapor. The psychrometric chart for air and water vapor shown here is fundamental to the practice of HVAC engineering, so much so that most practicing mechanical engineers have one on their desk at all times. The x-axis shows the air temperature, also known as the dry bulb temperature. This is the temperature reading of a typical thermometer. Moving along the x-axis is known as sensible heating or cooling. The y-axis shows the amount of water vapor in the air, also known as the absolute humidity. Moving down the x-axis is known as latent cooling. As air gets warmer, the amount of water vapor it can hold increases, which is shown as the curved line on the far left. As air cools, it moves left on the x-axis as sensible cooling until it reaches full saturation or 100% relative humidity. At this point, the air is holding as much water as it can. If it gets colder than that, water will start to condense out of the air, a point known as the dew point. This condensation is latent cooling, lowering absolute humidity. You've seen this as dew on the grass after a chilly night following a hot, humid day, or as fog on the inside of the glass when you open a door in the frozen food aisle at the supermarket. In this graph, I've marked out the typical range of air that we find comfortable. This can vary by a range of factors such as season, typical outdoor climate conditions, clothing, and physiological factors such as body composition, metabolic rate, age, and sex. In commercial buildings, we need to provide ventilation with outdoor air. In a climate that experiences hot, humid conditions, it is not enough to just lower the air temperature with sensible cooling. The air needs to lose absolute humidity as well. Let's say it's 95 degrees Fahrenheit and 50% relative humidity outside. To cool down a space with outdoor air, we need to provide air that is colder and drier than room air. Typical HVAC systems cool the air down to 55 degrees Fahrenheit to have enough capacity in the air to keep any room in the building within the comfort range. In multi-room HVAC systems, some rooms need more cooling than others. If a room needs less cooling than the minimum allowable ventilation rate, the air needs to be partially reheated to keep the room from getting too cold. This simultaneous heating and cooling is a reason why many large buildings have heating loads on hot, humid summer days. If that seems like a waste of energy, that's because it is. There are better ways of designing multi-zone HVAC systems that don't have simultaneous heating and cooling. But you must keep in mind that the practice of HVAC engineering for most of its history didn't care about energy or emissions. It was about keeping people comfortable, and that's still the primary driver. These systems were engineered to have enough cooling capacity through ventilation air alone to cool down a towering glass skyscraper in the middle of a hot summer, and likewise have enough heating capacity to keep that same glass box warm on a frigid winter morning. In our example, we use energy in 4 ways: sensible cooling, latent cooling, sensible reheating, and the energy associated with moving the air. And it's a lot of air mass to move. We ventilate enough in typical commercial buildings to replace all the air in a room every 1 to 2 hours. The energy it takes to move air with a fan, the power it takes to move air with a fan or water with a pump is proportional to the cube of the flow rate. Many HVAC systems, especially residential ones, are cycling systems, meaning we turn on for a while until the set point is reached and then turn off. Let's say we have a fan that can either cycle on and off at 100% of flow for a total working duration of half an hour, or operate at 50% capacity for the full hour. It moves the same amount of air in both cases, but uses 4 times more energy over the hour when it's in cycling mode. Given that the amount of air needed to provide heating or cooling is usually more than needed for ventilation, it can be expensive in terms of fan energy to meet heating or cooling loads with air-based systems. The other thermodynamics principle I want to introduce is heat transfer. Heat transfer is fundamental to buildings. Much of the energy we spend on buildings is to keep them at comfortable temperatures, which involves transferring heat into or out of a building. We depend on insulated heat transfer boxes to keep our food cold, which are refrigerators. There are several means of heat transfer. Conduction is heat transfer through objects that are in contact, such as your hand on a hot stove. Convection is heat transfer due to fluid motion. You may instinctively use convection to cool down a spoonful of soup by blowing on it. Radiation is heat transfer through the emission of electromagnetic radiation. Thermal radiation is emitted by anything above absolute zero, and the rate of transfer between two bodies is dependent on their temperature difference. You may experience the sensation of radiative heat transfer if you stand in the sun versus the shade, and this is especially evident if you've ever experienced a solar eclipse. If a building had no heat transfer and no people or equipment inside, the air temperature would stay the same. Conduction heat transfer is one of the main sources of heating and cooling loads. Heat transfer is determined by the thermal conductivity of a material, the thickness of the material, the surface area, and the temperature difference across the material. Temperatures and surface area are determined by the climate and the building. The thermal transmittance, or its inverse, thermal resistance, is a property that can be controlled and is specified in building codes. Building energy code stipulates maximum U values for roofs, walls, windows, and floors, often broken out by climate zone. Insulation is more important for a building in Anchorage, Alaska than it is in Los Angeles, California. There are a variety of materials we use for insulation. Air and noble gases have low thermal conductivity, so most insulation materials involve restricting or trapping gases. Fluffy jackets, fluffy blankets, and furry animals all rely on this type of insulation. Conduction can be cut out completely by creating a vacuum, and this is the design intent of vacuum panels, though there is still radiative transfer and conduction through the supporting structure. A thin vacuum panel has the same insulative value as fiberglass bats a foot thick. But we don't just build with insulating materials. Wood, brick, concrete, and glass are all relatively thermally conductive. The best window you can buy will not be as good as a typical wall with insulation. Many architects struggle with this reality. Insulation is only as good as the contractor installing it. Bat-style insulation is both the most common type of insulation in residential buildings and the one with many installation issues. Contractors don't fit it to the cavity, they'll compress it, or they'll leave large holes. When there are large air cavities, air can flow through the insulation, reducing its effectiveness. Bat insulation can be installed well, as shown in the pictures on the bottom. Another issue with insulation is that it is only as good as the structure it's embedded in. Wood, concrete, and steel are relatively thermally conductive, and heat transfer will follow the path of least resistance. You can come close to seeing heat loss with the thermal camera. In the upper left, you can see heat transfer through the wooden studs of a house, and on the right, heat transfer through the concrete balconies on a high-rise. The bottom image here is a comparison of a simple wood stud wall with fiberglass bat insulation. Even though the insulation is rated as R21, heat transfer through wood reduces the effective assembly value to R14. Adding just an inch of continuous insulation to the outside cuts off this thermal bridge, which improves the effectiveness of the bat insulation, increasing the overall assembly value to R22. Exterior continuous insulation was required as of a decade ago in the 2012 version of the International Energy Conservation Code for residential buildings. Most US states still use the 2009 code version without the requirement because of pushback from the construction industry. Many cities and counties may opt to have better local codes than the state minimum.
Matt, there was a question in the chat about
yes, I see two of them.
Insulation is the most common, if you want to.
Yeah, so one other question, yes, this is being recorded and the slides will be shared. And what style is most common in residential buildings? Bat insulation, probably fiberglass bats. And in commercial buildings, it varies. There is some bat insulation in the walls and also continuous insulation on the exterior. So another major source of heat loss in buildings is from air leakage, also known as infiltration. This is driven by the stack effect. Similar to how air bubbles in water are buoyant, hot air is buoyant when surrounded by cold air. The result is that when it is cold outside, buildings tend to develop a negative pressure with respect to the outside at the bottom and positive pressure at the top. A pressure differential plus a hole creates airflow. On a cold winter day, a typical residential building may lose an entire volume's worth of air over 2 hours, and this effect gets stronger the colder it gets. This effect is significant and it is responsible for about half of peak heating load. Now that we've covered some building energy basics, we can go into how buildings use energy. We recently completed the End-Use Load Profiles project at NREL, which developed hourly annual load profiles for residential and commercial building end uses across the US. We calibrated against 15-minute or hourly utility meter data from millions of buildings from 11 utilities. The tools we used for this are ResStock and ComStock, which are models of the residential and commercial building stocks in the US respectively. They are composed of hundreds of thousands of energy models of representative buildings. The project webpage has more details on the methodology, the data viewer, and access to the load profiles. Here's a look at the energy and emissions breakdown for residential buildings. You can see why much of the focus is on heat transfer. Heating constitutes about half of the energy use and emissions. The other electric section in purple here includes lighting, plug loads, refrigerators, dishwashers, freezers, and other miscellaneous uses. You can see the breakout of the other electric section on the web viewer online. Here is a look at the electric load profiles for a typical housing unit in different locations, calibrated against utility data. On the left is a typical summer weekday, and on the right is a typical winter weekday. The black lines and surrounding dashed lines show the meter data from a utility and its uncertainty. Grid peaks are heavily determined by residential heating and cooling demand. Most electric grids in the US have an annual summer peak coinciding with peak residential cooling, though this may change soon in colder climates as buildings switch to electricity for heating. You can see the relative impact of electric heating in the winter load profiles for Tennessee, Florida, and South Carolina, which have a higher fraction of electric-based heating systems. Peak cooling tends to lag solar generation by around 3 hours. Winter peaks do not overlap with solar generation and will require other renewables or storage to meet loads in a zero emissions grid. We can drill down further to determine the causes of heating and cooling demand. You'll notice the blue section on the left, which is infiltration. Infiltration is half of the heating demand, with conduction losses contributing the rest. Solar gain through windows offsets a bit of the need for heating, and in a well-designed building can offset most or all the heating load, as we'll see in a few slides. For cooling, solar gain through windows and interior equipment causes most of the demand. So now is the good time to ask that poll question, where I'd like everyone to, we can pop that up. And to your best of your ability, how much electricity does your home or the place where you're staying, it could be an apartment, use in a given year? So if you could just fill that up, we have 8 people.
Obviously, if you're not in the US, you multiply by the conversion ratio and then 100. That makes sense.
Yeah. Okay, I'm going to close it in about 15 seconds here. Okay, so I'm going to end the poll now. So we can see there's a range here, 0 to 4,000. I'm in that bin, 8 to 12,000, over 16,000, and then half the people, majority don't know. Oh, I have to do something with the poll here. There we go. So what these load profiles don't do a great job of showing is the distribution in energy use, even between similar homes in the same location. So the x-axis here are these kilowatt hour per year bins, and so you can estimate, depending on these different utility regions, where you would fall. The lowest 10% of customers use about a third of the median, and the top 10% use between 2 and 3 times the median. This has consequences for efficiency programs and home energy retrofits. Energy conscious users are more likely to pursue energy efficiency projects, but have less absolute energy savings available to them. Now, looking at those survey results, we note that people that decided to take part of their weekends to attend a webinar on climate, we still had about half of people that didn't have a good idea of how much energy they use. And of those they did, we had a very wide range of energy uses. And I think the point I would make with this is that residential energy use, it's very cheap and it's often invisible, and people don't have a very tangible sense about how much energy they're using. So who are the lowest energy users? Well, the reality is that there are many residential buildings in the US that don't rely on the electric grid or fossil fuels for heating, and there are some buildings that are entirely off-grid. The idea is to lower heat losses to a level where solar gain coming in through the windows is enough to keep the house at a comfortable temperature throughout the winter. Passive solar design is a practice that has a long history in North America, perhaps best first exemplified by the Puebloans in the Mesa Verde cliff dwellings in Colorado. The cliffs shelter the buildings from rain and the summer sun, while allowing in lower angle winter sun. The high mass construction keeps the building warm for a while after the sun sets. Modern passive solar design started with the MIT Solar House in 1939. After the oil crisis in the 1970s, there was a huge surge in interest in energy efficiency and passive solar design. The energy efficiency expert Amory Lovins built his Snowmass, Colorado home during this period. The building is driven by a solar heated greenhouse where he grows several tropical crops, including bananas. This is in Snowmass, Colorado in the Rocky Mountains, and they're still skiing here in June. In the late 70s and early 80s, there were hundreds of thousands of passive solar residential and commercial buildings built. The Solar Energy Research Institute, now NREL, did substantial research on passive solar buildings and recommended energy code implementations to make this more standard practice. It never caught on. The public lost interest in energy issues in the 80s. And if it had caught on, we'd be having a very different conversation about electrification today. Passive design moved over to Europe in the 80s, carrying on the research work from North America in passive buildings. This culminated in the Passive House standard, originating in Germany in the early 1990s. The standard is as much a guide as it is a goal, emphasizing continuous insulation without thermal bridges, airtightness, and mechanical ventilation with heat recovery. The US has since adopted its own version of the Passive House standard, and there are now thousands of buildings built to the standard in the US. This standard is finally getting serious attention as a possible goal for residential energy code. The air tightness requirement of 0.6 air changes per hour while the house is depressurized to 50 pascals, abbreviated ACH 50, is particularly difficult to reach. Newer versions of the International Energy Conservation Code require air testing to reach just 3 or 4 ACH 50. Prior to about a decade ago, buildings weren't even tested for air tightness, and typical buildings before that time are around 6 to 10 ACH 50 or higher. If you build a building to the Passive House level of care and add a right-sized amount of winter sun-facing glazing, you can likely do without a heating system. Let's look at a simplified case of heat loss using just the wall conduction component. This will give a sense of what heating electrification will mean for the grid. This example is a 2,000 meters squared, or about a 2,100 square foot, 2-story house near New York City. We can calculate the heat loss during peak winter heating versus the wall assembly effective thermal resistance. The passive standard gives a total peak heat loss allowance of 2,000 watts for the entire building, including wall, roof and window conduction, air leakage, and ventilation air, which isn't shown here. A typical new home uses that entire allowance on wall losses alone, which is this new construction in the blue here. A typical residential building, which is this yellow, that does have insulation, switching from a gas furnace to a heat pump will add around 1 to 1.5 kilowatts of peak winter demand to the grid operating the heat pump just from wall losses. Wall losses may be about 15 to 20% of the total heat loss, so a heat pump heated home may have around a 7 kilowatt peak winter demand. Scaling that up, 1,000 homes is 7 megawatts, and 1 million homes is 7 gigawatts. There are 3.5 million homes in New York, and the state electric grid currently has a 24 gigawatt winter peak. So that gives you a sense of the possible increase on the electric grid by electrifying residential building heating. Now let's switch over to commercial building energy use. Commercial buildings are a lot more complicated than residential buildings. There are many kinds of buildings spanning a wide range of sizes, and they require mechanical ventilation, which means complicated HVAC systems. Half the energy is spent on HVAC end uses. Lighting levels are also much higher in commercial buildings. A closer look at the end use breakdowns shows that HVAC end uses are split between heating, cooling, and ventilation. Commercial building energy gets less attention because it's less visible. Ventilation fans are hidden, even though they use more energy than interior lighting. Another aspect of commercial buildings is the concentration of energy use in a few buildings. 50% of commercial buildings in the US are under 10,000 square feet, but account for only 5% of total floor area and 12% of energy use. The 20% of buildings over 50,000 square feet are 70% of the area and 60% of the energy use. And someone asked what percent of greenhouse gas emissions can be attributed to residential commercial building energy use. I would estimate probably around 40%. Drilling down into the causes of energy use, ventilation air, shown here in gray, is the largest source of heating and cooling demand in commercial buildings. Most HVAC systems are air-based, providing heating and cooling by transferring hot or cold air into a space. Dehumidifying ventilation air is a major component of cooling in hot and humid climates. Here are the weekday load profiles during different seasons in several utility regions. I'm only showing retail buildings here, which have a higher lighting load relative to other commercial buildings. One thing worth noticing is the load profile is decently matched to solar energy production. That's part of the reason why on-site solar is now required on most new buildings in California. Another thing to notice is that the nighttime loads are underestimated. Even leaving lots of lights and equipment on and having a significant fraction of buildings providing continuous ventilation can explain the nighttime load in our models. We suspect that this has to do with malfunctioning HVAC systems. Our energy models assume all mechanical components and controls are working correctly, but that's rarely the case. Another aspect that we don't capture well with models is the variation in energy use between buildings of the same type. Energy use intensity is a common measure in commercial buildings, which is the annual site energy divided by the floor area. Here, I'm showing just electric EUIs with kilowatt hours as the unit per square foot. A more common measure is to use total energy measured in kilobTUs. From our analysis of utility meter data, we found that buildings of the same type can easily have an EUI either 3 times less or greater than the median EUI. Well, I forgot to include the legend on this graph. I'm sorry. The blue is our models. The yellow here is our AMI, which is the meter data. And the green here is from a commercial building energy consumption survey, which is a national survey of building energy use. Our variations in our models do account for a wide range of differences in buildings, especially the efficiency of building components, depending on the energy code at the time of construction. From energy code, we expect there to be about a 2x difference in energy consumption, but this alone doesn't explain such a wide range. So CBEX is just answering a question in chat. CBEX is just a survey of buildings, and it's from individual building owners and what's reported. With AMI data from Comstock, we got that directly from utilities. So we think that the main source for our lack of diversity in energy use comes from underestimating problems in mechanical design, components, and controls in commercial buildings. In the top left image, you can see an attempt at insulation. This is a dropped ceiling with a conditioned office below. The thermal and air barrier should be this ceiling, but the insulation was moved around and there was no air barrier. If you look closely, you can see an open hole to the outdoors in the background. On the bottom left is an image of exposed, uninsulated outdoor ductwork running from the HVAC system. You may recall from earlier how good metal is as a conductor. I'd estimate that around 5 to 10% of the heating and cooling energy in commercial buildings is lost to exposed ductwork like this. These images are from a California Energy Commission study that was looking at problems in small rooftop HVAC systems. They found that the HVAC systems themselves have a lot of issues, especially economizers. Economizers are a device that opens the outdoor air damper to provide 100% outdoor ventilation air when the air is cold enough to provide cooling. Economizers routinely break, with around half of economizers having some serious control issue, such as the dampers being stuck open or closed, or the temperature set points set incorrectly. Just like with passive house standards in residential buildings, we have been building net zero energy commercial buildings for a while. Net zero buildings match the amount of energy they use annually with production from rooftop or on-site solar PV. Some examples here are the Half Moon Bay Library, which I helped design, which has an EUI of 22 and has been operating at net zero. A typical library uses twice as much energy. The buildings where I work, the RSF at NREL, was one of the first net zero lab buildings in the US and includes a data center. It has an EUI of 35. A typical office building with the data center uses easily twice as much energy. Another example net zero building is the ASHRAE headquarters. ASHRAE is the professional organization for building mechanical engineers and authors commercial building energy codes. The design process is relatively straightforward. Make a good thermal envelope with a reasonable amount of glazing to lower heating and cooling loads. Match it with well-designed daylighting and an efficient HVAC system, then add solar PV. Many buildings can be retrofit to be net zero energy. There was a recent pilot program that replaced HVAC systems on small commercial buildings in the northeastern US. They used dedicated outdoor air systems with energy recovery, providing only the amount of air needed for ventilation and meeting heating or cooling loads with a variable refrigerant flow system. Buildings in the pilot saved 45 to 85% of their HVAC energy use. The savings comes from moving a much lower volume of air and recovering most of the energy from the exhaust air. Building code is moving towards net zero energy by 2030. This is already the case in California, which has its own energy code. Building energy codes originated in California thanks to the work of Art Rosenfeld, who authored the first efficiency standards. Energy code is typically based on setting minimum performance standards for specific building components, such as HVAC equipment, lighting, and the building envelope. But there can be significant differences in how a building is put together with these components, especially with respect to HVAC systems, as we saw on the last slide. Minimum component performance standards for HVAC equipment is similar to setting efficiency targets for vehicle classes, but not dictating whether a person should buy a small sedan or a large truck. There are limits to how efficient energy code can reach through using the best technology on a building component basis. Energy code will need to become more holistic and more reliant on performance-based approaches to meet the zero energy target. So what can we take away from all this? First, and most importantly, we've had the technology and knowledge to design efficient buildings for a while. There is generally an issue of low public knowledge around building energy. Most people don't know how much energy they use or where, and this is especially true for commercial buildings where building owners don't know to fix serious problems. Owners tend to value things like all glass buildings and fancy interior finishes more than the quality of the building envelope or HVAC systems. A major contributor to this is the split incentive problem, whereby the people that pay the capital costs for the building and the equipment are not the ones that pay the energy bill. Mechanical equipment lasts for decades and is usually replaced on an emergency basis, prioritizing immediate equipment cost, availability, and speed of install over energy efficiency. Mechanical designers and contractors are a conservative group and only recommend and install systems they are familiar with. They are used to providing systems for typical buildings with bad envelopes and haven't updated their perceptions of appropriate sizes for mechanical equipment. They are driven primarily by the desire to avoid callbacks and not energy efficiency. Joe Listberg, who is a key person behind the improvement in building insulation and air leakage standards, sums it up best when he says, some of the most effective technology transfer to practitioners in the construction industry is through the legal profession. Besides building code, it's usually only lawsuits arising from mold or other issues that cause the construction industry to change practice. So I'm going to pause there for a second and open it up for some questions. And if you want to ask in chat or unmute yourself, you can do that.
I have one I popped in the chat. I'm going to ask. Basically, how much more, I'm assuming more, do the net zero buildings cost relative to the current building regulations? And like, is there like a time frame for when they almost like make that cost back over time based on lower energy consumption?
It very much depends on the sort of design. I would say you could probably do it for less than 20 or 30% increase in cost. A lot of it comes from shifting the costs of the mechanical system to the envelope. If you have a much better envelope, you have to pay a lot less for the mechanical systems. And it even unlocks some more efficient mechanical systems that don't have a very high sort of power capacity to them, but are otherwise very efficient. So for net zero buildings, yeah, I mean, we've seen very cheap ones being built. I know like the RSF, for instance, was built at pretty much what a normal building would have been built for. Let's see, other questions here. Yeah, so there's a point here that many builders start with sustainable goals, but then they end up sort of backing off from those. And I think a big problem from this is sort of people try to do efficiency or reach these standards on a component basis. So you really have to have a more holistic design, especially shifting costs to the envelope rather than focusing on the mechanical systems. And things can get value engineered out. So a big issue I've had in some of our design projects is some people would always try to get rid of the exterior shading that we had on the windows, but that was really important for reducing glare and really important for keeping the design cooling loads down so that we could meet the loads with our HVAC system and have that be efficient and low cost. But if people aren't seeing that whole picture, then they might try to get rid of that component. So regarding the low interest in building efficiency, it doesn't seem to attract attention. How do you make it cool? Pun intended. I'm not sure. It was cool in the early 1970s, and a lot of people built passive solar buildings. I think it's somewhat becoming cool again, but I don't think we can rely on just sort of popular interest for it, as we sort of saw with the first wave in the 1970s. I think this really needs to be a sort of code push to say you have to build a building that is going to be efficient and resilient and not have these big problems, especially for commercial buildings where it's just all about money. And there's only a small subset of the market that really cares. Okay, so let's move.
I had a question as well, kind of on that.
Yeah.
It was on like the split incentive problem. That seemed like particularly important because I can definitely see developers want to drive costs down because they know ultimately they're not going to pay the cost of the free rider problem. I guess, how do you think one would actually combat the split incentive problem?
I think, again, the answer is mostly codes. It's really tricky for existing buildings. And there's sort of this balance of how much do you push what are sort of known as the maintenance codes and sort of push that and force people to do it. But then oftentimes they'll just pass those costs on to renters or people that have a lease on the building. So there's definitely some balance in managing that split incentive problem and trying to not overwhelm the cost transfer to the occupants. But I think this is largely about code and just setting standards. I think for most buildings, they can do a lot and they can get paybacks on the order of months with just some simple commissioning and making sure the HVAC systems function properly. But it just doesn't get a lot of attention. So a reference point is that, you know, a typical building might have around $1 or $2 per square foot in energy use per year. The salaries for their workers are easily 2 to 3 orders of magnitude more than that. So from like a total operating cost perspective, like the energy is just not a thing that the owners really care to think about. Okay. Any other questions here? Yeah, someone just making a good point. Okay, so let's shift to this next part of the talk here, part 2, and that's about the electric grid. So globally, most of electricity generation comes from fossil fuels, particularly coal and gas. Coal has been on the decline in recent years as it is more expensive than new gas plants and renewables. The US generation fleet is composed of many older thermoelectric coal and nuclear plants built in the 1970s and 80s. In the early 2000s, there was a building spree for natural gas plants and more recently wind and solar. Many coal and nuclear plants are nearing the end of their expected life. For coal plants especially, it is increasingly cheaper to retire them early and replace them with renewables than it is to keep them running. In the US, renewables have now surpassed both coal and nuclear power in annual generation. Coal use is less than half of what it was a decade ago. This is the primary reason for the decrease in total US greenhouse gas emissions over the last 2 decades. The major story in electric generation is the cost decline of wind and solar. Utility solar is now less than $1 per watt, with a price decline of 20% for every doubling of installed capacity. Onshore wind has seen similar price declines. This price decline has been routinely underestimated by energy agencies, most notably the International Energy Agency. Recent forecasts continue to underestimate the learning rate and overestimate the achievable minimum price they anticipate for solar PV. The graph here on the left is showing projections of the cost projections by the EIA and the dashed lines, and the actual is with the dots here. And on the right here is an estimate of the minimum costs they expected, or the price floor they expected for solar PV. As a result, IEA and other agencies have consistently underestimated the growth of solar PV capacity installed worldwide. These projections are from their stated moderate scenarios at the time that they were made and are still used to make claims about the future. Solar and wind are now much cheaper than other generating technologies per megawatt hour over their life cycle. Coal-based generation hasn't seen price declines with further adoption, and nuclear generation has a negative learning rate in most developed countries. Short duration battery storage is also coming down in price. Lithium-ion batteries are showing a faster learning rate than solar and are now being included on 1/3 of solar installations to time shift generation into evening hours. Wind, solar, and batteries, WSB, as it's known in the industry lingo, accounted for about 90% of new generation in the US over the last several years, especially last year. Prices for new wind and solar are so cheap, they are often cheaper than the marginal operating costs of thermal electric generators. This means it is cheaper to shut down an existing thermoelectric plant and replace it with new wind and solar than it is to continue operating the plant. Many coal plants in the US have retired because of this, with assistance from the Sierra Club's Beyond Coal campaign to make sure public utility commissions are properly accounting for the costs of generations. Many electric grids in the world have a deregulated energy market, meaning the electric generators are different from the companies that own the transmission lines and distribution network. An independent system operator, or ISO, runs the market. Energy markets typically have several components, and these vary by the specific ISO. There is usually a day-ahead market where generators will commit to how much energy they can produce at a specific time tomorrow. There is an hour-by-hour or real-time bidding and correction market, and there is a capacity market where companies will indicate that they can bring a certain amount of capacity in several years to meet future load. In an open energy market, generators will bid in how much energy they can produce at what time and at what price. Variable renewables with no marginal operating cost, or they have no marginal operating costs, so they populate the initial load. Generators bid into the market at their marginal operating cost, including nuclear plants, combined cycle gas plants, and finally, inefficient coal or gas peaker plants. Once the load is reached, all generators will be paid the price of the last marginal generator to meet the load, known as the clearing price. Solar and wind fill out the bottom of the market, and as much more come online, it lowers the clearing price and forces more thermoelectric generators out of the market. Some thermoelectric generators that take a while to ramp up and down may be forced to sell their energy into the market at a loss during certain times if they can't shut down. While solar and wind are the cheapest sources of energy, they are variable, thus the name VRE, or variable renewable energy. There is a limit to how much VRE can contribute to a grid before it hits intermittency issues and stops displacing thermoelectric generators. More VRE displaces higher cost generating options, which also lowers the market clearing price. In highly transmission constrained areas in California with lots of solar, or in the Midwest states with lots of wind, there can be negative energy prices during some hours of the year. In most of the country, however, renewables are still a small portion of total generation, so they are still displacing thermoelectric plants, particularly coal. California is among the furthest along in decarbonizing its grid. There was a time last April when they met 95% of their grid load with renewables. The grid operator CAISO has some nice graphics that show the generation mix in real time. This is the graph of the load profile on September 8th of last year, which was their peak day. Demand is light blue, and the net demand minus VRE is in purple. California has an early fall peak driven by cooling. It doesn't get very hot in the big cities, so cooling is instead driven by solar gain through windows in September when there is a lower sun angle. Solar significantly lowers net demand in the middle of the day, but cooling load remains high as it starts to drop off. The result is that lots of other generation needs to come online quickly, known as the ramp rate. This is tricky to coordinate and has been getting steeper. Here is a look at the same day broken out by generation source. Gas plants provided most of the generation for the early evening peak. This shows that when considering the total system cost for a decarbonized electric grid, we need to look beyond just the lowest life cycle cost for energy generation. Electricity needs to be used or stored immediately when it is produced, and there needs to be enough capacity to meet demand at all hours. The complement to cheap renewables is highly dispatchable and rampable firm generation sources. In California, that means gas generation. Many gas peaker plants are only used during peak hours and are quickly being displaced with cheaper short duration battery storage. So how can we predict what the hourly generation profile looks like in the future and in other parts of the country? To do this, NREL developed a tool called Cambium, which is a dataset and visualization tool for grid modeling outputs. There are several grid, transmission, and dispatch models used to make estimates of the generation composition, energy costs, and emissions for a range of scenarios out to 2050. The modeling software optimizes for the lowest cost grid under various scenarios, including full or partial decarbonization. This is what the emissions profile looks like for California in 2030. The spring and summer months operate on renewables during the day, with batteries and gas plants supplementing wind in the evening and nighttime hours. The highest emissions occur during the grid peaking days in September. Fewer daylight hours during the winter months means a narrower generation window for solar. In a full grid decarbonization scenario, a simplistic approach would be to build out enough renewables to meet demand even during summer and winter grid peaks. This is an expensive option, and dispatchable, rampable firm generation sources can lower costs by providing peaking capacity while still using low-cost renewables from most generation. A recent NREL study investigated this question in detail and found that for the US, the cheapest grid would have 57% of energy generation from renewables. To decarbonize, the grid could reach 80% VRE renewables with minimal further cost. Beyond that, there is increasing overbuilding and curtailment of renewables to meet load during peak hours. Costs rise sharply after 90%, at which point decarbonizing with renewables effectively costs around $100 per metric ton of CO2 or higher. We can look at high renewable penetration scenarios in more detail to help understand the costs and needs going from 80 to 100% decarbonization. Firm generation sources constitute around a third of generation capacity, but only a small fraction of total annual generation. As we increase the decarbonization requirement, firm generation switches from gas combustion turbines to batteries and renewable-based hydrogen combustion turbines, with hydrogen produced by renewable energy. Hydrogen combustion turbines are just one of many possible zero-emission firm energy generation sources. While it would be nice to have cheap zero-emission firm generation options available today, we can reach high levels of decarbonization without it. A scenarios analysis of grid decarbonization shows that a fully renewable grid by 2050, which is this yellow line here, would cost about 30% more than the lowest cost option. Moving the timeline up to 2040 would cost about 40% more. Allowing other non-renewable low or zero emission sources to count, such as nuclear or carbon capture and sequestration on fossil plants, has interesting results. While these can allow for a fully decarbonized grid for less than a 20% cost increase, they do entail more cumulative emissions by 2050, as seen by the orange dots in the figure on the right. This is because allowing these options to count as zero emissions allows more existing fossil generation to operate while still following the zero emissions trajectory, forestalling the build out of renewables. In the context of cumulative emissions, it may make sense to de-emphasize the 100% decarbonization goal and instead focus on getting to 90 or 95% as quickly as possible, which we can do without substantial increases in electricity costs. At present, renewables are transmission constrained, and there is a backlog of hundreds of billions of dollars of renewable energy projects waiting to be built once transmission is ready. Storage is another option for firm generation, and another recent NREL grid study looked at decarbonization using storage. There are three general types of storage. Short duration storage is under 10 hours, able to charge and discharge quickly at high round trip efficiencies. Lithium-ion batteries are an example. Long duration storage is for multiple days, 10 to 100 hours. There are two varieties here, one with lower power and energy costs, but lower efficiency, such as compressed air energy storage, and one with higher costs and higher efficiency, such as pumped hydro or flow batteries. Lastly, there is seasonal storage operating on timescales over 100 hours. An example is stored hydrogen with combustion turbines. This study looked at two grids, CAISO and MISO, which is the Midwest system operator. The left graph shows the proportion of different kinds of storage needs as renewables make up a larger percentage of generation. MISO is more dependent on seasonal storage than CAISO. Both don't need seasonal storage until they reach between 90 and 95% of renewable generation. These images here are heat maps that show the storage state of charge, with red being full and white being empty. The top four heat maps are for different kinds of storage for CAISO, and the bottom for MISO. An interesting aspect is that sometimes high efficiency short or long duration storage is used to charge seasonal storage. Seasonal storage is largely used to balance out energy demand in the winter months with lower solar generation. While these grid studies are helpful to understand future decarbonization scenarios, they are quite popular in academic journals right now, it is helpful to understand their limitations. Most grid studies use the NREL technology baseline assumptions or the IEA assumptions, which may underestimate the ongoing price declines of solar, wind, and batteries. Studies often treat the grid load as exogenous, meaning demand is a fixed load profile that grows a certain percentage over time. This misses all the things happening on the demand side of the grid, including vehicle electrification, electrification of building heating, and gains from building efficiency. Building Energy Code is targeting net zero by 2030, which means the building stock will be slowly changing over to rely less on the grid for bulk energy and more as a means to handle energy imbalances. The LA100 project is another 100% renewable energy study that considered a wider range of loads and options to meet demand, but just for the city and county of Los Angeles. They are looking at ways to get to 100% on a shorter timeline by 2030 or so, as they've committed to shut down their multi-gigawatt gas plants in a few years. This study was probably the first of its kind to consider the impacts of meeting future demand with building energy efficiency. We found that much of the capacity to replace the gas plants can come from efficiency standards and utility incentive programs for air conditioners. This study also included an estimate of the impact of electric vehicles, which reaches 90% EV adoption among light-duty vehicles by 2050 in the highest demand scenarios. With heating electrification and vehicle electrification and load growth, we anticipated annual electricity use to nearly double from 25 to 45 or 50 terawatt hours. An interesting note about the inclusion of electric vehicles is the timing of grid peak changes depending on the scenario, sometimes shifting to the middle of the day. Shifting car charging more to the peak solar period can reduce the need for firm generation or storage during non-solar hours. One other direction the grid may go is that other industries may take advantage of excess renewable generation, reducing curtailment and allowing more of it to be built economically. If an industry's costs are dominated by operational energy costs more than capital costs, such as with cryptocurrency mining, they can act as a grid resource, turning off when spot prices are high. Texas is already using Bitcoin miners to help balance the grid in this way. There could be a range of other uses for cheap energy, such as producing renewable fuels, including hydrogen, nitrogen fertilizer for agriculture, materials from electric processes like aluminum, and even direct air capture of carbon dioxide. So I want to pause there and ask if there are any questions on the grid. I can probably answer questions for about a minute or two here.
I've got one. One was about saying like the marginal cost of operating coal plants is now higher than almost building new solar or onshore wind. So it's like there's no point for coal power plant owners to keep doing that. I guess, is that true just in the US or like globally as well? Because I guess, I don't know if TerraPractice, like one of their main things is repowering coal plants. And do you think is that true globally or just in the US?
I think, so there have been a few studies on this. After the talk, I can probably track down the one that showed that probably around 50 to 60% or more of coal plants, could be retired, and it would be cheaper to replace them with renewables. I think one of the challenges here is that a lot of utilities that are vertically integrated, meaning they control the whole pipeline of generation, transmission, and distribution, they can do what's called self-scheduling. So they determine which generators they run and when, and they often tend to decide to run their coal generators plants just to keep them economical and keep them running. So yeah, I think a lot of coal can be replaced, but there are other considerations beyond just costs that are sort of keeping them operating. So another question here, grid, what kind of topologies will we have? More distributed grids and energy storage, and of course, renewables and intermittent sources, and also more EV stations. Yeah, so I think there's a lot of ways the grid could unfold. I think there's a point for some buildings, especially residential buildings, where the value the grid provides to the building becomes less than the value the building can provide to the grid. And that sort of flips things on its head. And then now there's this question for, say, residential buildings, if battery packs are cheap enough or they're efficient enough at the building where they don't, they only need a few kilowatt hours of storage to just be off grid, there's not really a case for them to connect to the grid. And so, I mean, I have seen that in some newer, like very high-end residential buildings. Actually, it's more common. I think Vermont has a program where they will, instead of running a power line all the way out to a house, because that can be very expensive, they will set the homeowner up with solar and some batteries, and they'll own that and then they'll sell that to the homeowner. And that saves them having to run out a power line. And so that, I think, are some of the things that we might see in more rural locations, especially. Do you think products like O-Power and Oracle and AER from Watt Time work to change demand during peak hours? What are other answers to the issues you've posed so far? I'll get to some other answers. But yeah, so O-Power and these are sort of things that will they might have some control within the building, or they might have some behavioral changes that can influence when people use energy. And these do contribute. You can basically have a whole bunch of homeowners that are part of these programs, and then these companies can sort of bid that in as sort of virtual power that's available that they can turn off or reduce demand when the utility requests it. And these are actually, in some recent legal rulings, they are allowed to bid in as capacity to these energy markets. They can say, you know, you pay me this much money and we will reduce all this energy use at these times. I think I'll get to this in a second, I think those can be somewhat higher cost options, but they do definitely work. And they could be an option for the sort of firm negawatts, as they're called, or you know, subtracting demand. Okay, so continuing on here so we can finish in time. Buildings are a huge component of the grid, so total cost to decarbonizing the grid will depend heavily on how building efficiency changes over time. Utilities currently spend about $6 billion per year on efficiency programs. Compare this to the spending on new generation, mostly renewables, which is around $80 billion per year. The cheapest source of energy efficiency comes from improving building codes and standards. It is much cheaper to have a building use less energy in the first place than to pay for efficiency upgrades for equipment being replaced later. Consumer and commercial rebates for efficient appliances or LED lighting are also a cheap source of savings and constitute the majority of total program savings. Whole house retrofit programs, which entail installation and mechanical system upgrades, are more expensive, but can achieve greater savings per project. Envelope improvements beyond attic insulation are especially expensive once a building is built. Low-income programs are the most expensive, largely because they require additional spending on health and safety issues, and the utility usually pays the entire cost of the upgrades. We can also see behavioral feedback is also listed as an option here of just pursuing efficiency through feedback programs or behavioral feedback programs. Building code is still being evaluated on a total energy savings basis. Improvements to building efficiency standards are justified if the energy cost savings is greater or equal to the incremental cost to meet the standard. And that's this connection point here of the marginal standard compliance cost with the energy cost. As we've seen from the grid analysis, bulk energy costs are decreasing in the near term with renewables, and the benefits of building standards increasingly depend on when the energy is saved. If we accounted for the reduced grid peaking capacity from improved building standards, that would allow more spending on building efficiency, particularly building envelope performance. And it would allow building efficiency to participate in the much larger grid capacity market rather than just relying on marginal efficiency program spending. There were also resiliency benefits shown in yellow here to better envelope standards. There is some point where the pipes won't freeze during a grid outage, and another point where the building will be able to maintain thermal comfort. Resiliency may become much more important as we switch from multiple major energy streams, oil, gas, and electricity, to just electricity. At that point, the consequences of extended grid outages becomes much more severe. But resiliency currently isn't valued. Maybe it will be in the future. It took a while for things like plumbing, electricity, and air conditioning to be seen as important parts of what makes a home. Looking from a global perspective, by 2050, there will be an estimated 2 to 3x growth in the number of buildings worldwide, largely occurring in developing countries in the tropics. This will create a surge in cooling demand and subsequent electricity use. Luckily, many of these countries have excellent solar resources and do not have to worry as much about seasonal storage needs because solar generation is relatively constant over the year and there aren't significant heating demands. They can probably reach a 95% plus emissions-free grid with some combination of wind, solar, and batteries alone. But more efficient cooling technology will go a long way to reducing emissions, especially emissions from refrigerants used in common vapor compression-based cooling systems. There are a variety of newer cooling technologies at various phases of commercialization. Indirect evaporative cooling here in the upper left works by spraying water into the air, cooling it down, and then running it through a heat exchanger to cool down the incoming airstream. This can only provide sensible cooling, but does so very efficiently and can meet cooling needs in dry climates. Radiant sky cooling uses selective materials to reflect incoming short-wave solar radiation, but stays open to long-wave thermal radiation, allowing radiant heat rejection to the sky. These panels can cool down a working fluid to 10 to 15 degrees Fahrenheit below the ambient temperature. Both of these are commercialized technologies increasingly used in current building projects. Separate, sensible, and latent cooling systems are a broad class of systems that cool air sensibly with one method, and then use a desiccant to remove moisture from the air. Lastly, there are non-vapor compression cooling technologies like thermoelastic cooling that uses the properties of some materials that gain or release heat when expanded or compressed. These can be a direct replacement for vapor compression systems, but have not yet been commercialized. The big picture is that we can decarbonize electricity about 80% of the way with solar, wind, and batteries, and we can do so at equal or lower cost to our current generation mix. There are a lot of contenders for that last 20% of decarbonization. Wind and solar may become cheap enough that it makes sense to overbuild and curtail them. Building efficiency can mitigate much of the need for generation, particularly during peak hours, and buildings can operate as virtual grid resources, reducing unimportant energy uses when needed. Electric vehicles contain substantial battery resources and can time their charging when is most convenient. New energy uses can change the load shape significantly, especially if their costs are energy-driven and modulate accordingly. Where firm generation is needed, zero-emission generation or storage may provide the needed peaking capacity. It will largely depend on which technologies can be built cheaply enough to compete with efficiency, demand reduction, and demand shifting. While there is tremendous economic momentum towards decarbonization, this occurs amidst a policy background that has strong preferences for incumbent generation technologies. Utilities, especially vertically integrated ones, earn a profit by building generation. They therefore have an incentive to delay cheap renewables to allow more time to pay down debt on their thermoelectric plants and earn profits from building new plants. First Energy in Ohio recently successfully bribed state lawmakers to give a multi-billion-dollar bailout to their struggling nuclear plants and some coal plants as well, while getting rid of the state's renewable portfolio standard. At the federal level, utilities and fossil interests have far outspent clean generation sources in annual lobbying dollars. The results are reflected in the federal budget requests, with as much money going to coal carbon capture research as the entire energy efficiency and renewables energy budget, which includes solar, wind, building efficiency, and a range of other technologies. Advanced nuclear reactors get nearly twice as much funding. The point is that if a decarbonized grid is eventually a policy goal that gets passed into law, the technologies that comprise the grid may differ significantly from the lowest cost option. And while I would allocate R&D funding differently if I were in charge, I think the R&D budget becomes less relevant the sooner we aim to decarbonize the electric grid. Biden has a goal of 2035, which is sooner than the technology and our current R&D pipeline can reach widespread commercialization. R&D funding has been used as a distraction by some who are interested in protecting dominant energy industries to hinder widespread deployment of the cheap zero emissions technologies that are already available. So that was quite a lot to think about. I'll try to answer some questions here. Homes factor into the emissions. Let me see if I can just read these really quick. Impact of modular homes. Yeah, so I think these will help. I mean, broadly, there is a significant need to just build more housing. Modular homes are great because you can build them in a factory. And so the quality control standards, especially on the performance, is a lot better. And you can justify spending more on the envelopes, especially. So I do think those are going to become more popular. And we're actually, in the group I work at NREL, we're actually working with a lot of different modular home companies, trying to help them design their efficiency standards for what they're building, and also looking at pairing them with renewables and batteries. So in the last few minutes, I want to sort of zoom out here, and I want to shift attention to more broadly thinking about climate change as a cause area. So climate change is unique among cause areas for three reasons. First, attention. The public is broadly aware of the problem, even if they don't appreciate the scale or challenge in reaching zero emissions. There is a dedicated United Nations body focused on climate change, the IPCC, which holds major conferences attended by all countries and has been operating for decades. The second aspect here is funding. There are billions of philanthropic dollars spent every year on the problem, and dozens of mature nonprofit institutions and foundations focused on climate. Governments and private industries are spending hundreds of billions per year on mitigation and to some degree adaptation. That's arguably comparable to the amount spent annually on ending extreme poverty. I'm not sure that there are many remaining opportunities on the clean tech pipeline of basic R&D, venture capital, equity, and commercial debt that aren't already well funded by non-EA aligned governments and private or public sector institutions. The third aspect is complexity. Because of the scope and pervasiveness of fossil fuels across modern life, it takes deep technical and policy knowledge to analyze interventions. Compare that to other cause areas. Farmed animal welfare gets much less public attention and has philanthropic funding in the tens of millions of dollars per year. It has relatively clear interventions that can be understood and advocated for with a basic level of knowledge. Risks from artificial intelligence require comparatively more technical expertise, but there is near zero attention given to it at the United Nations level, and the Effective Altruism community contributes nearly all the philanthropic funding. Global health and poverty get similar attention and funding as climate change, but the interventions are relatively clear: economic development, direct cash transfers, and targeted basic health provision. Climate change is one of many causes we care about, and about half the Effective Altruism community thinks it should be at or near the top priority in the recent EA survey. However, people that are more highly engaged or have in the community for longer tend to rate climate change as a lower priority cause area. There are several possible explanations for this, but I think one contributing factor is that some people shift their attention from climate change to other cause areas as they get more involved. So given these characteristics of climate change, I think a few suggestions follow. First, there is a chance that you'll decide to prioritize other causes in the future. If where you give has changed considerably over the last few years, especially shifting cause areas, it may be wise to put your money aside and donate later. If you want to focus on climate exclusively, my second suggestion is to spend your efforts trying to influence policy change or influence how other environmental philanthropy is given and save your money for EA causes with less public support. If you feel compelled to give money, my third suggestion is to consider more deeply why you are concerned about climate change. If, for example, you are concerned about the human impacts of climate change, know that many of the devastating impacts are not locked in. If you look at the recent World Health Organization report on projected climate deaths, many of these are from malaria or other poverty-related diseases. We could eradicate malaria and extreme poverty by 2050. That's within our power with enough sustained effort. And in case any of you are Malthusians, a recent Nature paper showed that eradicating extreme poverty would increase global greenhouse gas emissions by less than 1%. Climate impacts a lot of little things, and so that raises this question: do you focus on mitigation, which reduces damage a little bit in a lot of different areas, or do you focus on one area and reduce damage a lot? I'm not entirely sure which is right, but I'm leaning towards the idea that $1 spent on malaria eradication and $1 on habitat conservation will have more impact on well-being than $2 spent on mitigation. If you really want to spend on mitigation, my third suggestion is to wait for better recommendations from the current effective environmental organization, namely Founders Pledge and Giving Green. There are about 4 full-time employees, plus maybe another 4 to 6 part-time employees between them, and they are moving about $1 million of funding each. This is comparable to GiveWell 15 years ago in number of employees, analysis output, and money moved. GiveWell recommended Population Services International then, and I think they would say their best giving options just a few years later were at least an order of magnitude better. My fourth suggestion, if you really want to spend on mitigation now, is to look at major mature funders in the climate space. The Climate Works Foundation is a good example. They give over $100 million annually in grants, ranging in size from about $20,000 to over $1 million. They likely know of a few smaller efforts that they wanted to fund but passed up on because they were too small. And I think this is an area where perhaps someone like Giving Green or Founders Pledge could step in. So my apologies if this part of this talk was underwhelming or discouraging for those who wanted to figure out where to donate. I think there could be some effective giving opportunities within the climate space, but it will take a bit of analysis to find them. So my thoughts on this are guided by a few points. First, I think adaptation is categorically neglected. Many people, organizations, and whole countries think that their responsibility ends at reducing their own emissions to zero. Wealthy countries haven't met their commitment to provide poor countries with $100 billion annually in adaptation funding they were promised. The real adaptation needed is in the range of trillions of dollars, and most of the billions that have been provided are in the form of loans and not grants. I think we should focus on emissions in poor countries because they don't have money for expensive mitigation projects, as well as focusing on emissions that are projected to increase substantially or are accelerating. This means not focusing as much on electric generation per se, even though it's still very large. Electric generation emissions are dropping across the developed world and will soon start dropping in developing countries too. Compare that to emissions from plastic production or meat consumption, which are rising. So what falls out of this are a few ideas. I think there can be a lot of good in promoting building standards and better cooling technologies in growing tropical regions. This is one of the few areas where I think R&D dollars can really help because there will be enough time to get those technologies through the R&D pipeline into the market as those places are growing. Funding academic professionals to improve national adaptation plans, restricting single-use plastics and formalizing waste management in poor countries, funding plant-based meats, particularly cow replacements, and finally, looking at natural feedbacks. Natural feedbacks don't fall under anyone's direct responsibility, and some occur outside of territorial boundaries. So these include wildfires, desertification, permafrost loss, and methane clathrates. So we made it. Thanks everyone for staying and listening to all that. There was an enormous amount of content that I presented there. You can message me if you have further questions or you want sources for anything I presented, and I'll drop my email in the chat in a little bit here. I also have a blog on WordPress called Watson Wagers. I haven't published in a while as I was finishing my doctoral degree, but I do hope to publish more regularly. So I'm just going to drop my email in the chat and still have some time for some questions. I'll try to get to some that I didn't answer already. What about recommending giving green? Yeah, I mean, as I said with giving green, and I think some founders pledge, I think they have their headspace in the right place, but I think they're just like, only a few people that are working on it. And I think there's just a lot of things they haven't considered yet. And so as I mentioned with that GiveWell analogy, I think their recommendations, once they get some staff, can be a lot better in a few years. So I would actually more recommend funding them directly, like especially Giving Green, to help sort of grow their analysis capability rather than just trying to get money out the door right now. Because I think they'll find a lot better options. The Malthusian Effective Annual. What about distribution of emissions from rich countries? Yeah, so a lot of the emissions are in rich countries right now. And it's quite unfair. And I think, I think we can see that with like sort of the focus on, say, mitigation dollars just spent in rich countries versus like trying to end extreme poverty. It is very unequal, and I think it'll take some time to sort of correct for that. Looking at degrowth and sort of how essential different things are, including CCS. Yeah, so I think in the very long term, like there will be degrowth considerations. I think like equitable growth right now is very important, especially for very poor countries. I think we will probably run into some like very growth-centered issues that we want to address growth directly, probably on the 50 to 100-year time scale. Carbon capture and sequestration, I think it's tricky, and I think the policy design on that is very important. So I think it's probably going to be a necessary component for something like cement, where there's really not great alternatives. I think a lot of other industries don't necessarily require it to decarbonize. I think another aspect of that is like currently the way that they're structured, and I have a post on this on the EA forum, or a comment on it on one of Giving Green's posts around the tax credits offered for carbon capture and sequestration. So they first allow it for power plants that you can use CCS. And second, the amount that they're giving is very high. Carbon capture and sequestration for power plants, it doesn't capture all the emissions. It captures maybe about 70 to 80%. The only working plant, which is in, it's up in Canada, I think they've only captured around 50% of their emissions because they had some issues with getting the technology to work. And so those are not zero emissions. They're low emissions, but they're not zero emissions. And I think as I looked at those other studies, I think they could just be very high cost, and they might sort of forestall sort of just building out more renewables sooner. So I think there's a lot of risk associated with allowing power generation to use carbon capture and sequestration. I do think that industry should, have full access to that at that full, $85 per ton that I think the current credits are going for, especially for cement. So what do you think Getting Green needs to do to better get better at analyzing, and what would be a good use for the funders? I think a lot of this is just getting a wider variety of experts in different fields. So the Climate Works Foundation, for instance, they have like dozens and dozens of employees that each are specialized in different areas. And I'm not sure if we need like an entirely other organization to do that. I think there is usefulness to having the EA angle. But I think coordination with some of these other major foundations that are giving the money could go a long way towards finding some of the gaps that they analyzed. And I think in the short term, that's like finding the gaps for these major established funders that are already pumping $100 million per year out could be a good place to look. So access to rare earth materials. Do we have enough rare earth materials? So I didn't address that in the talk. I figured it might be a question that people would ask. If you go on to David Roberts' blog, he posts on Canary Media, and he has his own blog called Vaults. He talks about critical materials there. There are some constraining materials. I think like lithium and cobalt, I think are two key ones. There are some resources that we could develop. So for example, the Salton Sea here in California, or in the US, I'm actually based in Colorado. And I think another aspect is there's a lot of other technologies that are shifting sort of chemistries to rely less on them. And the amount of material they're actually using the material efficiency is improving greatly. So I do think there may be some slight issues with it, but I don't see as like a complete bottleneck or like, we're going to be fundamentally limited in like the cost declines on renewables. Any other questions?
I think everyone needs like 2 days to digest this. I'm like watching recording like several times. I think there's like so many good graphs in there. I just like get my head in.
Yeah, I did go through it pretty quick, and I expected that this is going to be the sort of thing that you listen to it once, you maybe get 50% of it, and you have to watch it a few more times to get to a greater percent of understanding. So yeah, but thanks for recording it.
And to run yes, I'm going to email out the recording probably on Monday or Tuesday, so tomorrow, Tuesday. So,
and I believe it's posted on YouTube as well. So
yeah, it'll be on YouTube. So watch as many times as you want.
Excellent.
It's been an amazing talk. Thank you.
Great, thank you. Were there any questions I didn't answer, or anybody that has some perhaps more counterpoints or things to what I presented?
I have a question from before on the coal plants thing, actually.
Yeah.
Do you think there's some other reasons besides economic drivers or costs that might limit like coal plants going out of existence? Like, what are those reasons besides cost that might be like important factors for coal plant owners?
I'm not sure if it's necessarily for the coal plant owners directly. I think that some of the countries may have certain reasons to try to keep plants operating. I know in the US, a lot of that is around politics and around trying to maintain the jobs. In other countries, I think it's around sort of energy supplies and sort of making sure they have some sort of firm generation, even if it's really bad. Coal plants, can provide at times when solar isn't producing. It's very expensive to do so, and there are better options, but sort of in the near term, that might just be what some countries decide to do. I recommend tracking down that paper, and I can try to find it and send you the link on looking at the sort of cost comparisons of replacing coal with either wind or solar. Where can you find out what orgs ClimateWorks is giving to? They do have a grants database on their website. And I think it's the ClimateWorks Foundation. I think it might be tricky to find, but they do have that sort of their grants database listed there. Yep, James just posted it to chat. Thanks. Okay, excellent. Well, thanks everybody. I guess this was a smaller group today, but I hope more people will get to see the recording. And again, if you have any questions, just shoot me an email.
Thanks so much, Matt. That was, pretty incredible. It was so informative. So, thanks so much. And thanks everyone for coming, and see you around, hopefully.